This video is exercise 2-6, building a GLM model, generalized linear model. And we are going to examine the response variable. We are going to use new response variable from VS Bank data. That is target count number new products. This variable consists of the number of products with which each account enters the current campaign season. The range is from 0 to 6 and is measured on a count or integer scale. Like the integer valued target that was considered in the previous demonstration, the distribution of the count target is not a good fit for the assumption of normally distributed errors embedded in the linear model. It is restricted to be non-negative. It also has right skew, and not many customers enter the current campaign season with more than 3 or 4 products. The demonstration begins under the linear model assumptions. The effects of violating the linear model's assumptions are explored as well. The modeling framework is generalized to find the distribution and support that have the following properties. They are compatible with the measurement of the dependent variable, and they enhance the usefulness of the model. So let me first show you the distribution of the response variable. Maybe you can just open a new page like I did, or if you have not done so, you can just click on this plus page and go to data, and under VS Bank data, find the target count number. Right? So if you can scroll down and then target count number new product and just click on it, drag it to your canvas, then it is going to create a distribution table automatically. How simple is that? And you can see 1, 2, 3, 4, 5, 6, this count data, and it's severely skewed to the right, and it's not obviously it's not following the normal distribution. We cannot use log transformation either because it's not a large number. It's only 1, 2, 3, 4, 5, 6. And in this count data, it's kind of difficult to run any regression model. So the option we have is to use a generalized linear model and try to explore the relationship between dependent and independent variables. So let's do that. Let's open a new page like this, and let's go to object pane here and find under visual statistics generalized linear model. So drag it to the page, and then because we need to set the variables, let's temporarily disable auto refresh, and let's specify the variables. Response variable is target count number, so go to the bottom, target count number new products. That's response variable. Continuous variable is log RFM 1 to 12, as we have done before. Okay, that's your X variable or independent variables. Classification, we did that, category 1 and 2. And we also added interaction effect before, so RFM interaction too. Now let's click the options pane, and the default distribution is normal over here, and the link function is identity, which means normal distribution here. And an ordinary linear model is fit under the default settings of the general linear model. From the menu bar, let's enable auto refresh and see what happens. and it ran the result, and we see that AI sees 1 million, over a million, and all those observations were used. Also, under display, let's go to display, and let's use stack so that we can see more in details. And let's go to residual. Residual gives us a very good hint about the data and how this model is doing. And as you can see here, there's a pattern in this residual negative correlation between the residual plot and the predicted values. Let's change this one to standardized Pearson residual. And the pattern has become clearer, and the darker the color is, the more frequency we have. So 10,000 or 99,000 observations belong to this area. The linear model assumption of constant error variance seems to be clearly violated here because we see negative correlation. And the variance of the residuals is negatively correlated with the magnitude of the prediction for the count value target. Another problematic aspect of this plot is that there seems to be a pattern in the residuals. This might be an indication that the model does not notice all the available signals in the data. That is, some of the systematic variation in the data is not incorporated in the explained variation of the fitted model. It is in what is supposed to be the random or unexplainable variation. So let's take a look at the assessment model as well over here. So we see this observed model, observed graph line is flattening out, and predicted average, this blue line, is higher than predicted average between 20 to 75 or 80ish, and after 80ish is significantly lower than observed average. So from this assessment plot, we see that clearly, this model is not the best. We can tell here. If you like to, you can maximize this toolbar and then see the statistics more in details. Click on type 3 test and see if all of them are significant. And all of them are less than 0.01, so it's the p-value. In terms of all these variables that we used in this model, they are statistically significant. Let's also click the Fit Statistics tab here, and Fit Statistics, and from here we can see the details of the Fit Statistics. Also, you can just explore the dimensions and iteration history, convergence, Fit Statistics, parameter estimate. This one gives you the coefficient of each variable and their significance.